Hello everyone, I am Dr. VRAO. From the lecture 58 of thermodynamics, we came to know that delta H and delta U are identical or same in case of solids and liquids. And in case of gases, these two are differ by equation, that is delta H is equal to delta U plus delta N RT, right. So, in case of gases, delta H and delta U are differ by the equation delta H is equal to delta U plus delta N RT. Now, in this lecture we are going to learn concept of cause and effect, cause and effect cause and effect. What is this cause and effect? When we can claim cause and effect, right? So, when two events occur at same time in the same place, then we can call it as cause and effect. I repeat, when two events occurs at the same time in the same place, then we can call it as a cause and effect situation, right. One such cause and effect is observed in chemistry as well as in physics, that is heat and temperature. Heat and temperature. When we transfer certain amount of heat to the system, that causes increase in temperature, right. When we supply or when we transferred heat to a system, that results a rise in temperature of this system, where heat is cause and its effect is rise in temperature. I repeat, where heat is cause and its effect is rise in temperature. That means when we cause to transfer heat to a system, its effect will be seen in the rise in temperature, right. So, Q, that is heat and temperature, where heat is cause and temperature is its effect, right. So, when we cause to supply Q amount of heat, to the system, its effect can be seen in the rise in temperature, right. So, that is Q is directly proportional to, then we can say that Q is directly proportional to rise in temperature. That rise or change, that can be written as delta T. So, Q is directly proportional to delta T, that is cause is directly proportional to effect, or heat is directly proportional to change in temperature or rise in temperature, right. So, Q is proportional to delta T and Q is equal to some constant. After removing this proportionality, we can we should embed what is it called constant. That constant is C into delta T, where C is the heat capacity of the system, Therefore, C, we can write C is equal to Q by delta T, okay, where C is the heat capacity of the system, So, heat capacity of the system can be defined as amount of heat required to rise the temperature of the system through 1 degree centigrade, I repeat, see, heat capacity is amount of heat required to rise the temperature of the system through 1 degree centigrade. That is called heat capacity. that is where C is called heat capacity. And from this equation we can conclude that another statement, that is when Q amount of when Q amount of heat will given to the system, it will rise the temperature of the system, if the heat capacity is large, right. So, I repeat, if where C is equal to Q by delta T, this equation tells you another thing, that is when if we pass Q amount of heat to the system, that will rise the temperature of the system to a small extent if the heat capacity is large, and vice versa. That means Q by delta T is a positive quantity where C is positive. For example, if you assume Q by delta T is a positive and it is a large value, that means Q amount of heat, by supplying Q amount of heat to the system, that will rise the temperature of the system to a small extent, that will rise the temperature of the system to a small extent, provided if the heat capacity is large, and this is vice versa. That means if heat capacity is low, if heat capacity of the system is low, that Q amount of heat will not rise the temperature of the system, right. So, Q amount of heat will rise the temperature of the system if heat capacity is large. Okay, if heat capacity is small, that Q amount of heat will not rise the temperature of the system, right. So, C is equal to Q by T. So, where C is heat capacity, that is amount of heat required to rise the temperature of the system through 1 degree centigrade. For infinitesimal changes, for small changes, we can write it as dQ by dt. For infinitesimal changes, we can write C is equal to dQ by dt, where Q is a path function. We know that Q is a path function, work and heat are path functions, where Q is a path function. So, therefore, C is also a path function, that is heat capacity is also a path function, right. So, Q is a path function, therefore, C is also a path function. Therefore, conditions such as constant pressure and constant volume have to be specified in defining the path for measuring the heat capacities. I already told you, if the heat capacity of the substance is rise, then the supplied amount of then the Q amount of heat will rise the temperature of the system. If the heat capacity of the system is small, then Q amount that is transferred, that is supplied Q amount of heat will not increase the temperature of the system. Okay, this is very important, that is if C is large, then this Q amount of heat will rise the temperature of the system. If C is small, that is his heat capacity is small, that Q amount of heat will not rise the temperature of the system, right. So, heat capacity C for infinitesimal changes, we write C is equal to dQ by dt, where dQ is, that is Q is a path function, therefore C is also a path function, therefore heat capacity is also a path function. And one more thing is that when heat capacity is path function, since heat capacity is path function, the conditions such as constant pressure and constant volume have to be specified in defining the path for calculating the heat capacities, because basing on the heat capacities we can define the what is it called, we can observe the what is it called, effect, right. So, heat capacity values are very important in deciding the cause and effect relation, right. Okay, so C is equal to dq by dt. So we have to specify the constant volume and constant pressure conditions as Q is a path function and C is also a path function. So heat capacity at a constant volume, heat capacity at a constant volume, right, heat capacity at a constant volume. At a constant volume. What is heat capacity? C, that is represented by dq by dt at a constant volume, dq by dt at a constant volume. From the first law of thermodynamics we can write from first law we can write q is equal to delta u plus w, and we can write that this is a pressure volume work, we can write PdV. So we are conducting at a constant volume, so volume changes are 0, that is dV value is 0. If it is dV value is 0, this equation that is 0, therefore this at constant volume dV is equal to 0. So this is equal to du and q is equal to delta u, then it is at a constant volume. So heat that we are supplying at a constant volume is equal to internal change in internal energy. So therefore C is equal to in case of Q, that is du by dt, that is du by dt. Okay, du by dt, we can write this like du by dt, right. So this is the change in rate of change in internal energy system, internal energy of the system with temperature, right. This indicates heat capacity at a constant volume. Heat capacity at a constant volume is defined as rate of increase in internal energy of the system with temperature. So heat capacity at a constant volume, that is rate of increase in internal energy of the system with temperature. Okay, now heat capacity at constant volume, heat capacity at constant pressure, constant pressure, right. So we know that q is equal to dq by dt, dq by dt, and we know that q is equal to delta u plus w, delta u plus w, and we know that h is equal to u plus pv, h is equal to u plus pv, and dh is equal to du plus pdv. Okay, du plus pdv, right. So in this equation we can write this du is delta u plus pdv, delta u plus pdv, right, delta u plus pdv, right. So next du is equal to, I can write du is equal to dh minus pdv. Therefore du, you substitute this equation in this that is q is equal to du means dh minus pdv plus pdv. This pdv get cancelled, that is heat capacity at a constant pressure, that is heat we are supplying at a constant pressure is equal to dH. Therefore, C is equal to, we can write dH by dt, dH by dt at a constant pressure. Okay, now we can write this dq, this can be written as actually why we are not writing the dq, because we cannot write dq and dw, because q and w are path functions, q and w are path functions, q and w are path functions. Therefore, we cannot write them as exact differentials. Okay, you please keep in your mind, Q and W are path functions. So, we cannot write them as exact differentials. Of course, we can write them as an exact differentials, right. So, Cp is therefore, Cp is rate of increase, that is rate of increase in enthalpy of the system with temperature. So, heat capacity at constant pressure is rate of increase in enthalpy with temperature, right. Now, relation between this Cp and Cv. Now, relation between Cp and Cv, we know that enthalpy H is equal to E plus Pv, H is equal to E plus that is U plus Pv, U plus Pv. For 1 mole of gas, we can write the ideal gas equation, Pv is equal to RT. So, instead of Pv, we can write RT. So, H is equal to du plus RT. Differentiating the equation with respect to temperature, that is dH by dt is equal to du by dt plus R. Okay, already we know that dH by dt, that is increase in enthalpy, rate of increase in enthalpy with temperature, that equals to Cp, heat capacity at constant pressure, and increase in internal energy, rate of increase in internal energy with temperature, that equals to Cv, heat capacity at constant volume, plus R. Therefore, Cp minus Cv is equal to R. So, the relation between Cp and Cv are, this is Cp minus Cv is equal to R, where R is equal to 2 calories, where 2 calories Kelvin inverse mole inverse, right, and or 8.314 joule Kelvin inverse mole inverse, right. That is the value, that is Cp minus Cv, that is Cp minus Cv, that is the difference between Cp and Cv is equal to work done by 1 mole of gas with the increase of 1 degree centigrade. That is difference between Cp and Cv, difference between Cp and Cv is equal to work done by 1 mole of gas when heated to 1 degree centigrade, right. Okay, and one more thing that you should keep in your mind is that Cp is always greater than Cv, because at a constant pressure gas expands as well as gas works, right, but at constant volume gas expands, gas works only, right. So, at a constant pressure, you simply remember one point, at a constant pressure gas expands as well as it works. Okay, so Cp is always greater than Cv, right. And one more thing is that what is the Cp values, the Cp of heat capacity at constant volume, heat capacity at constant pressure. Okay, because as heat capacity is a path function, we have to specify the constant volume, constant pressure for defining the path for measuring the heat capacities. In case of, especially in case of gases, especially in case of gases. So, we have to calculate the heat capacities of gases for monoatomic gas and diatomic gases. Okay, always Cp is equal to, or Cv is equal to F by 2 RT, F by 2 RT, where F is the number of degrees of freedom and Cp is for diatomic gas. For diatomic gas, we can write Cv is equal to F by 2 RT, and for a diatomic gas Cp is equal to F by 2 plus 1 RT, right. So, with this formula we can calculate the Cv values and Cp values, right. So, where F is the degrees of freedom, where degrees of freedom means translational degrees of freedom, and rotational degrees of freedom and vibrational degrees of freedom. Okay, always we know the translational degrees of freedom are 3 along the 3 axis, and rotational degrees of freedom is 2, right? Because 2 we can rotate the molecule with end over end rotations with the 2 possibilities. Okay, and vibrational degrees of freedom are possible at only at high temperatures, not at moderate low temperatures. So this value is always 5 degrees of freedom in case of diatomic molecules. But in case of monoatomic gases, these values only translational degrees of freedom present. Rotational and vibrational degrees are not are absent in case of monoatomic gases. Okay, so Cv is equal to F by 2 RT in case of diatomic gases, Cp is equal to F by 2 plus 1 RT in case of diatomic gases, right? And one more thing is that ratio of heat capacities will give us an idea on atomicity of gases. That is Cp, the ratio of Cp to Cv, which is called as gamma. Okay, this value gives the information of atomicity of the gases. If it is comes out to be 1.66, that is a monoatomic gas. That is a monoatomic gas, right? If it is 1.44, it is a diatomic gas. And if it is 1.33, it is a triatomic gas. Monoatomic gases are again that H2, diatomic gases CO2, what is it called H2, monoatomic gases all what is it called halogens or monoatomic gases, monoatomic here, that is halogens inert gases, helium, neon, argon are monoatomic gases, diatomic gases H2, right, Cl2, and triatomic gases SO2, CO2, right? And this is all about heat capacity. But in practice, when we are doing problems, molar heat capacity and specific heat capacity are we always using the terminology molar heat capacity and specific heat capacity. Already we know that heat capacity C is equal to Q by delta T. Okay, so heat capacity is defined as amount of heat required to rise the temperature of the system through 1 degree centigrade. Okay, for example, molar heat capacity is defined as amount of heat required to rise the temperature of 1 mole of substance. 1 mole of substance is called molar heat capacity. That is, molar heat capacity is equal to heat capacity for 1 mole of substance. Heat capacity for 1 mole of substance. That is nothing. Amount of heat required to rise the 1 mole of substance is called molar heat capacity, right? And specific heat capacity. Specific heat capacity, we know that heat capacity C is equal to Q by delta T. That is, C is equal to Q by delta T. So, where specific heat capacity means amount of heat required to rise the temperature of 1 gram of substance through 1 degree centigrade, right? I repeat, amount of heat required to rise the temperature of 1 gram of substance through 1 degree centigrade is called heat capacity at specific heat capacity. Cv is equal to, that is specific heat capacity is equal to heat capacity per gram of the substance. Heat capacity per gram of the substance. Usually we can write this that is heat capacity is Q by delta T by M. That is specific heat capacity CSP is equal to Q by M into delta T. From this we can write Q is equal to specific C into M into delta T, right, delta T. Pass. Okay, so that is about heat capacity, molar heat capacity and specific heat capacity. Okay, among heat capacity at a constant volume and heat capacity at a constant pressure and constant volume, and heat capacity at constant pressure is always greater than constant heat capacity at constant volume, as at constant pressure gas expands as well as gas works, right. And one more thing is that this ratio, that is the ratio of heat capacity at constant pressure to constant heat capacity at constant volume, that gives the information about the atomicity of the gases. That is, if it comes out to be 1.66, that is called monoatomic gas. If it comes out to be 1.44, that is a diatomic gas, and if it comes out to be 1.33, that is a triatomic gas. Okay, and one more important point, that is heat capacity. Okay, heat capacity C is equal to Q by T. This equation tells you that for a given amount of heat that will rise the temperature of the system, provided if heat capacity is large. If heat capacity is small, that Q amount of heat will not rise the temperature of this system. Okay, so that is about heat capacity. And okay, I hope you all understand this lecture. Thank you for watching.